Hi, my name is Wei Han. Today I'm going to present my project, which is a development of Hillside land monitoring system utilizing IoT. So this is the poster of my project. So the system is the combination development of the three elements. So first is the multi-communication architecture, whereby they got two communications. First is the ESP32 communication between the sensor nodes and LoRa transceiver. Another one is LoRa communication for long-range transmission from LoRa transceiver to LoRa gateway. The second element is the communication performance evaluation in detail to compare both communications. So for analysis of ESP32 data loss and transmission range, and LoRa data loss, range, RSSI, and SNR under line of sight and non-line of sight conditions, including optimization of LoRa bandwidth and spreading factor. So the last is the IoT integration, whereby the sensor data is transmitted to a cloud platform for real-time visualization and monitoring. The objective of this project is to develop multi-communication monitoring system together with IoT method for landslide application. Second is to analyze and investigate peer-to-peer communication in terms of network topology in IoT network, data loss, range in line of sight and non-line of sight in multi-node landslide monitoring system. Finally is to enhance communication algorithm with acknowledgement protocol and make comparison to conventional technique without acknowledgement protocol. So this is the step-by-step on how to develop the system. So the first phase is to do the circuit development for the system, especially from the sensor nodes and also the LoRa modules. And then the next step is to do the communication performance test for the ESP32 communication and LoRa communication. So after that, then I will choose the suitable network topology, especially for the communication between the sensor nodes and LoRa transceiver. Then after select the suitable network topology, then I can decide how many number of sensor nodes can be installed to communicate in an optimized manner with the LoRa transceiver. So after develop all the systems and also chosen the correct adjustment settings for the communication, then I will do the initial test for the data transmission from the sensor nodes all the way to LoRa gateway. So after that, then I can do the integration of the IoT, which is from the LoRa gateway connect to the Wi-Fi to push the received sensor data to the IoT cloud, which is the Google Sheets. So this is the first results. So it is about the ESP32 communication performance. So they have two types of ESP32 communication, such as Wi-Fi point-to-point and BLE. So when it comes to the range test, the Wi-Fi point-to-point has performed better than the BLE in terms of the range in line of sight and non-line of sight condition. So specifically, the Wi-Fi point-to-point achieves about 150 meters in line of sight and also the 40 meters in non-line of sight conditions. So next is the experiment for the LoRa communication performance in multiple locations. So first is the in line of sight condition and also non-line of sight condition. So this is the detailed results of LoRa communication performance test. So as we can see that the SF12 has a stable variation in terms of the RSSI and SNR values in line of sight and non-line of sight from 0 meters to 400 meters compared to other spreading factor, which is shown that the SF12 has a more reliable communication for the data transmission. So next is in order to determine the exact maximum distance that the LoRa TX and LoRa RX can communicate together. So there is a model that has been used in this project, which is called Okumura-Hata model. So as we can see in the graph generated from the MATLAB, which is using the Okumura-Hata model theory. So from the graph shows that the maximum distance that can achieve is about 2.36 kilometers in one area, which is the suburban areas. So In the practical experiment, I already located the LoRa TX on the hillside and another one LoRa RX on the ground. So as we can see that the distance that between the LoRa TX and RX in the practical experiment was tested about 1.67 kilometers, which is within the distance simulated. So this is the final design based on the experiment and simulation. So the total number of sets of sensor nodes that can be located in the hilly area is about 5, and then the communication between the sensor nodes and the LoRa transceiver will be using the Wi-Fi point-to-point at most 115 meters of distance, and then the LoRa one end to LoRa another end, which is using the LoRa configuration of the spreading factor of 12 and also at bandwidth 125 kilohertz. The distance between the LoRa one end to LoRa another end will be at most 2 kilometers. So the ACK is also applied into the ESP32 communication and also the LoRa communication, is because the ACK is the protocol which will notify the transmitter confirming either the receiver successfully receives or not. If the receiver failed to receive for the first attempt, the transmitter will be notified to resend the same data at the next attempt until receiver receives successfully. So this helps to reduce the critical data loss for the landslide monitoring application. So this is the overall functionality of the system. So it starts by the 5 sets of sensor nodes transmit their own data to the LoRa transceiver. So after LoRa transceiver successfully receives all the data, then it will transmit to the LoRa receiver, then to the LoRa gateway. So after LoRa gateway successfully receives all the data will be pushed to the Google Sheets. So the Google Sheets will record based on the data parameters such as the node name, their data ID, their dates, and also the time. So next is the social design criteria. So the first is the community and stakeholder needs. So the system supports communities and authorities by providing early landslide risk monitoring, helping reduce damage in hilly areas. Second is the community industrial problem, whereby the addresses limited network coverage in hilly region by using LoRa long range, low power communication, which is suitable for remote monitoring. And the third one is the local circumstances and culture. So the system is designed for suburban and hillside environments, considering non-line of sight conditions with minimal environmental disturbance. And then number 4 is the human health and well-being. The system continuous monitoring enables early warning, improving public safety and disaster preparedness. And then number 5 is the safe and beneath materials, which is the system uses the low voltage, low power electronic components with no hazard materials, ensuring safe long-term operations. And number 6 is the rules and regulations, where the system operates within the licensed ISM bands and follows the standard electrical and communication safety practices. So overall, the system is developed to hybrid Wi-Fi point-to-point and LoRa communication for multi-node hillside monitoring. It's also a performance-based optimization of LoRa bandwidth and spreading factor. It is also a reliable long-range transmission using acknowledgement-based LoRa protocol. So the system can lowering the cost not just on long-range monitoring without cellular dependency, but is also referring to the architecture. It minimizes the number of LoRa nodes by using non-communication distances. Only one LoRa transceiver is required for multiple nearby sensor nodes, and LoRa repeaters are added only when necessary to extend coverage to the gateway. So there is also a scalable multi-node deployment for large hillside areas. It's also ready for cloud-based monitoring and early warning integration. So overall, the system has achieved 3 sustainable development goals. So first is SDG 9, which is industry, innovation, and infrastructure. Second is the SDG 13, which is climate action. And then the last is SDG 11, sustainable cities and communities. That's all for my presentation. Thank you.